We have not defined what is meant by the logarithm of a complex number. However, if we have a logarithm of a complex number, say log z, then it is desirable that the derivative of log z is equal to 1 by z. And by the chain rule, we would like to have the derivative of log f of z to be f prime of z by f of z. And because of this formal calculations which I just said, we would like to use the terminology log derivative to denote f prime of z by f of z. So, let me just write that. We will denote the log derivative, we will denote by log derivative of f. This is the formal definition that we are defining, the meromorphic function. So, this is for f on omega be a holomorphic function, and the log derivative of f is on omega, and that is going to be a meromorphic function, and the meromorphic function is nothing but f prime of z by f of z. So, notice that away from the zeros of f, this makes perfect sense. This is going to be a holomorphic function away from the zeros of f, and because the zeros are discrete, at zeros this is going to have poles, this is going to be hence a meromorphic function on omega. The log derivative is well behaved and consistent with what we would expect. So, for example, if f and g are two functions on omega, what can we say about the log derivative of f times g? So, what will we get if we look at fg prime by fg? By looking at the product rule, we will be able to write this as f prime g by fg plus fg prime by fg. So, away from again away from the zeros of f and the zeros of g. So, I will not write that again and again, it is understood. This is being written wherever it makes sense, and that is precisely equal to f prime by f plus g prime by g. So, notice that if we did have a log, this is exactly how log of f plus log of g would be, right, the derivative of that. Log of f plus log of g is log fg, and this is in line with what would one expect for a log derivative. Similarly, if you look at f by g by f by g, this f by g prime by f by g, this is going to be equal to f prime g minus f g prime by g square by f by g, which is g by f, which is going to be g times f, which is equal to f prime by f minus g prime by g. Again, that is in line with what we expect, because log of f by g is something like log f minus log g. Of course, I have not defined what a log is till now. So, all these references to log are hypothetical and based on our existing knowledge of the logarithm defined on real numbers, positive real numbers. We will come to defining the logarithm later, but right now, even if the word logarithm is not referred to at any point of time, the log derivative can be defined in this manner, and the log derivative satisfies these conditions. These are the things to keep in mind. Let us look at what happens when our f and g are polynomials. So, consider a polynomial of the following type: p of x to be equal to say a times z minus z1 up to z maybe z minus z1 to the power d1 times z minus zn to the power dn, where zi's are distinct, and let q of z be the polynomial maybe b times z minus w1 to the power e1, z minus wn m maybe to the power em. Suppose we have two such polynomials where zi's are distinct and wi's are distinct, where zi's are distinct in the sense that zi is not equal to zj for I not equal to j, and similarly wj's are distinct. So, Wj1 is not the same as Wj2 for j1 not equal to j2. Suppose we have this and we are interested in p of z by q of z, the rational function r of z given by p of z by q of z. So, away from w1, w2 up to wn, this makes perfect sense. This is a function holomorphic in that domain away from the zeros of q. And let us now try to find out the log derivative. The log derivative here is just going to be equal to, then by using an induction argument, one could argue that r prime of z by r of z, this is going to be equal to d1 by z minus z1 plus d2 z minus z2 plus all the way up to dn by z minus zn. This is in the case of the things which appear in the numerator, and below this is going to be minus of e1 by z minus w1 minus all the way up to minus of em by z minus wm. So, simple check, you can actually sit down and check that this is indeed what is happening using the two checks that we have already done. Using these two, one can very easily conclude that this is what is going to happen. When we described holomorphic functions initially, power series rather, we noted that there were many properties of polynomials which generalized to power series, which turned out to be holomorphic functions. In fact, complex analytic functions are locally having a power series expansion. So, many of the properties of polynomials generalized to holomorphic functions, and such a relationship holds between rational functions and meromorphic functions as well. So, we see that when the rational function is of this type, our log derivative is given here. Let us now try to see what happens to the log derivative of holomorphic function, how it behaves. So, let us consider the log derivative case by case and analyze what happens. So, to do that, let us start with some function f which is defined on omega away from set of singularities. Let f be a function holomorphic on omega minus s. Then suppose z0 is a point in omega such that f is holomorphic on z0 in a neighborhood of z0. That is what it means to say f is holomorphic on z0, and f of z0 is not equal to 0. Then there is no confusion here, f prime by f is then holomorphic in a neighborhood of z0. So, in such points we do not have any confusion. Now, let us see what happens when f has a 0 at z0. So, this is one case. What happens when z0 is in omega, in fact omega, and z0 is not in s. Let us take that particular case. We know that it is, and so it is already taken care of here. We know that it is holomorphic. So, it was already in omega minus s anyway. So, this means that f is holomorphic at z0 and f of z0 is equal to 0 with order m, let us say. What does that mean? That means that f of z is equal to z minus z0 to the power m times g of z, where g of z0 is not equal to 0. That is what it means for z0 to be a 0 of order m. And then we have f prime of z is basically m times z minus z0 to the power m minus 1 into g of z plus z minus z0 to the power m times g prime of z. And when we divide it by f of z, we end up with z minus z0 to the power m here, and here we end up with again the same thing, z minus z0 to the power m and g of z. So, hence we get the log derivative of f to be equal to m by z minus z0 to the power 1 plus g prime of z by g of z, and by noting the previous case, this function is holomorphic on z0. Let me say is on z0 to denote that it is holomorphic in a neighborhood of z0. So, notice that it is something similar to what happened here. Here at every point z1, z2, zn and so on, it has a simple pole, and the residue of the log derivative of r at zi's is equal to di, and the residue of the log derivative of r, the rational function at wi's, it is going to be equal to minus of ei's. When the pole appears, the residue is minus ei, and that is something similar that is happening here as well, right, at least in the case of zeros which we have just checked. There is a simple pole at z0 which is a 0 of f, and the residue is equal to the order. So, we have in some sense, using the log derivative, reduced the problem of finding the order of a 0 to finding the residue of this particular function f prime by f. That is the case when we have f of z0 is equal to 0. Now, the case when z0 is in S and it is a removable singularity is very similar. So, let me not z0 be a point in S and z0 be a removable singularity. Removable singularity is a singularity which can be removed, and after it is removed we get a function which is holomorphic across z0, and because of that its behavior at the removable singularities is exactly the way it behaves at points where it is holomorphic. Then f prime by f behaves as above. So, let me not elaborate there. It will have a removable singularity if it is the first case, that when the extension does not vanish, and it will have a simple pole when the extension of f vanishes at z0. So, that is why it is being referred to as above. The more interesting case comes up, maybe not the more interesting case, but the interesting case will be when z0 is a pole and z0 be a pole of order m. Then what happens is that we have z minus z0 to the power m times f of z is equal to g of z, where g does not vanish. G of z is not equal to 0 in a neighborhood of z0. And because of that, we can write f of z to be equal to the meromorphic function g of z by z minus z0 to the power m. Then what will be the log derivative? Log derivative is going to be f prime of z by f of z, which is going to be equal to g prime of z by z minus z0 to the power m minus of m times g of z by z minus z0 to the power m minus 1, minus of m plus 1, this is going to be m plus 1 rather, and divided by f of z, which is g of z by z minus z0 to the power m. So, this is going to be equal to g prime of z by g of z, which is just some holomorphic function, minus m times g of z cancels off, and what is left is z minus z0. Therefore, when z0 is a pole of order m, where m is greater than or equal to 1, the log derivative of f is equal to a function which has a simple pole at z0 with residue equal to minus m. So, we have certainly considered what happens when f has a meromorphic function in various cases that arises here. We have not considered all types of singularities, of course. For example, we have not addressed the case when z0 is an essential singularity, in which case the behavior could be quite arbitrary, and when f is say identically equal to 0, the log derivative is not defined at all. So, we have not considered all cases. However, we have taken care of all the cases which will be relevant to us in stating our next theorem, which is called the argument principle. Let me state down the argument principle, and then we will discuss more about it. Let omega be an open set in be an open set in C, and f be a function meromorphic on omega, defined on omega, such that it has zeros of certain orders at z1, z2 up to zn, such that f has zeros of order d1 to dn. F be a meromorphic function. So let me just write that very carefully. And f be a meromorphic function. So it's defined on omega minus some singular sets. And let's see what happens. Zeros of order d1 to dn at z0 to, or rather z1 to zn, after removing the removable singularities. So there are only finitely many zeros with orders d1, d2 up to dn here, and such that e1 to en, and it has poles, and f has poles of order e1 to em, let's say, at points w1 to wm. So the setup is quite straightforward. We have a function f which is defined on omega minus w1, w2 up to wn, and each of these wi's are poles with order e1, e2 up to em respectively, and also f vanishes exactly at z1, z2 up to zn. No other point does f vanishes, and the orders are captured. Order of the 0 of f at zi is captured by di. So this is our function f. So our goal in this argument principle is to compute the zeros in some sense using the log derivative. And in order to do that, let's pick a gamma be a closed curve in omega which is null homotopic. So closed curve which is null homotopic in omega, such that the zeros and poles of f do not lie on gamma. Zeros and poles don't lie on gamma, or the image of gamma rather. Then the conclusion tells us that 1 by 2 pi I times the integral over gamma f prime of z by f of z dz, this is equal to summation di w gamma of zi, where I is going from 1 to n, minus summation j is equal to 1 to m ei w gamma of wj rather, where w gamma is the winding number. So this is a theorem where a combinatorial question of counting the number of zeros and poles is being converted into an analytic argument. So by computing the integral of f prime by f over gamma, we will be able to compute the number of zeros and poles in the interior of gamma. Let me just draw a picture to capture whatever we just wrote. Suppose we have a omega in this manner, and suppose our curve gamma is with the dark green. Suppose we have a curve like this, and suppose we have some points. The points let's capture with zeros are being captured with blue. Suppose there are points like this, z1 to zn in this manner, and say pink is capturing the poles. Then our theorem tells us that, notice that only in this region will be the winding number non-zero. Outside this region the winding number is going to be 0, so the contribution there does not come up. So in this region whatever be the number of zeros and poles with the multiplicity can be captured by this integral. So, di times the number of times it winds. So, in this case the winding number is 1. So, summation di minus summation ei is going to be this integral. That is what the argument principle tells us. Let us give a proof of this. The proof is quite straightforward. There is nothing much to do here. We have already done all the necessary work. We can write f of z to be equal to z minus z1 to the power d1 up to z minus zn to the power dn by z minus w1 to the power e1 all the way up to z minus wm to the power em times g of z, where g has neither zeros nor poles in omega. G has neither zeros nor poles in omega. So, this is done by successively using the fact that zi's are zeros and wi's are poles of f. So, maybe an induction argument can help us conclude this, and once we have this, we will be able to write our log derivative in the following manner. F prime of z by f of z is just going to be then d1 by z minus z1 plus up to dn by z minus zn, just like how you would have computed in the case when it was a rational function. The same computation here will tell us that this is what we will finally end up with. Wm plus g prime by g, g prime of z by g of z. Now, g prime by g is a function which is holomorphic on omega, and let us now look at what our curve had as properties. It was a closed curve which is also null homotopic in omega. So, if you now look at the integral, if you take the integral of this is going to be the integral of this function dz, and this is going to be equal to, or maybe we can put a 1 by 2 pi I here to capture the winding number, that is the goal. The right hand side is going to be equal to 1 by 2 pi I times the integral of d1 by z minus z1 dz, which is basically d1 times the winding number of the curve gamma around z1 up to dn, the winding number of curve gamma around zn, minus e1 times the winding number of the curve around w1, em times the winding number of the curve around wm, plus the integral of g prime by g over gamma, which by Cauchy's theorem is equal to 0. And this is precisely what was written in the statement of the theorem. Notice this is precisely what is being written in the statement of the theorem. Now, if we actually explore the left hand side, if you look at the integral of the log derivative of f over gamma, one can actually check that this is in fact equal to the integral of f prime of gamma of t. So, if gamma is defined from a to b, so consider gamma to be a contour, a piecewise smooth curve, then f prime of gamma of t, gamma prime of t dt by f of gamma of t. And by the chain rule, this is just equal to the integral of f composed with gamma prime of t dt by f of f composed with gamma of t. So, define our curve sigma from AB to C given by from A to B. Sigma of t equal to f composed with gamma of t. And what we have just shown is that let me put 1 by 2 pi i's the above is just 1 by 2 pi I, this is equal to 1 by 2 pi I integral over sigma dz by z, which is equal to the winding number of 0 around sigma. And we just showed that the winding number of sigma around 0 captures this description of the number of zeros and the number of poles. A remark before we go further about what happens when f does not have poles. Suppose f is holomorphic on omega with just the zeros, z1 to zn, and suppose you take, if you take a curve gamma, gamma be a simple closed curve, in that case the winding number is either 0 or 1, simple closed curve which does not pass through zi's. Then the number of zeros in the interior of gamma, simple closed curve, null homotopic. Then the number of zeros in the interior of gamma where the image of the homotopy is defined, in that particular region the number of zeros counting multiplicities is equal to integral of f prime by f over gamma, 1 by 2 pi I times the integral of f prime by f over gamma. Just write that, then 1 by 2 pi I times the integral of f prime by f gives the number of zeros of f counting multiplicities. In the interior, maybe I should just mention it this way, in H of 0 1 cross AB, where H is the homotopy from gamma to the constant curve. So, if you look at the number of zeros in that region, so if this is our curve, this is the region I am referring to. In the interior of this curve, we will be able to capture the number of zeros by looking at integral of f prime by f. We will be using this very shortly in some really powerful theorems, but before that let me also state one theorem regarding the stability of zeros. The Roshes theorem tells us that if you perturb our gamma to any other homotopic curve, then the integral is going to be the same, and therefore the number of zeros of any function, if you perturb our curve gamma a bit, is not going to change. Number of zeros and number of poles, the difference is not going to change. Similar is the case with functions f. If we perturb our functions a bit, perturb our holomorphic functions a bit, I will tell exactly what that means, then the difference of the zeros and the poles will not change. So, if you are focusing just on holomorphic functions and not bothering about meromorphic functions, the number of zeros will not change if you change the function a bit. So, that is the next observation, which is going to be about the stability of the zeros. So, let omega be an open set. Let me just create the premise for you. Let omega be an open set and gamma be null homotopic closed curve in omega. Suppose H, so this is from AB into omega. So, suppose H from 0 1 cross AB into omega be a homotopy, let us put a 0 here, from gamma 0 to gamma 1, homotopy of closed curves. From gamma 0 to gamma 1. So, we now have two pictures, two curves here. Gamma 0 is something like this, and gamma 1 is something like this. Suppose we have homotopy in this manner. Let us say that along these lines is how the homotopy goes. Of course, there are no holomorphic functions yet involved in this story. Suppose f0 and f1 are holomorphic functions on omega such that there exists a function, let us call this function capital F, from 0 1 cross omega, there exists a continuous function from 0 1 cross omega into C given by f of 0 comma, not given by, such that f of 0 comma z is equal to f0 of z and f of 1 comma z is equal to f1 of z. So, we have a further suppose that these zeros are well behaved. Suppose further that for all s in 0 1 we have the extra condition that f of s comma h of s comma t is not equal to 0. So, notice that h of s comma t is just gamma s of t. So, the function, it basically tells us that f of s comma dot, this particular function which is defined on omega, does not vanish on gamma s. This is precisely what is being demanded, right. Gamma s is basically h of s comma t. So, in particular f0 does not vanish on gamma 0, f1 does not vanish on gamma 1 and so on. That condition is being, so basically if, for example, all the zeros of f0, f1 or rather for that fs, for the f subscript s for that matter lies in this region, this particular condition is satisfied, the condition and the hypothesis is satisfied. The conclusion here is that then the number of zeros of f0 in the interior of gamma 0, remember that gamma 0 is null homotopy and therefore, there is a homotopy which homotopes gamma 0 to a constant path. So, when I say interior of gamma 0, one can think of the interior as the interior of the image of the homotopy which takes gamma 0 to the constant path. So, the number of zeros of f0 in the interior counting multiplicities is the same as the number of zeros of f1 in the interior of gamma 1. So, notice that the only assumption was about gamma 0 and gamma 0 was assumed to be a null homotopic curve, and because it is a equivalence relation, gamma 1 is also going to be a null homotopic curve and the interior of gamma 1 is also going to be defined in exactly similar manner as of now. We have not proved the Jordan curve theorem. So, the interior does not make sense if I do not make it precise. The definition of the interior right now is by considering the homotopy, look at its image, and that is the interior of that image is what is going to be the interior. And the theorem that we just wrote down here about stability tells us that the zeros of f in the interior of gamma 1 and the zeros of f1, zeros of f0 in the interior of gamma 0 and the zeros of f1 in the interior of gamma 1 are going to be the same counting multiplicity. So, if you perturb our gamma a bit and if you perturb our f a bit, the zeros will not change. The proof actually, even though the statement is so big, the proof is going to be extremely small. So, if you come up, we will see that the number of zeros, this integral is being captured by the winding number of sigma around 0, right. And that's precisely capturing. There are no EIs here that will capture the number of zeros along with multiplicity. So let me just note that down. The number of zeros with multiplicities of F0 in the interior of gamma 0 is given by 1 by 2 pi I times the integral f prime of z by f of z dz over gamma 0, which we had noticed is the same as the winding number of sigma. Let me call this sigma 0 here of 0, sigma 0 around 0, that is the number of zeros here, and similarly the number of zeros of f1 with multiplicity in the interior of gamma 1 is given by W sigma 1 of 0, where sigma 0 is the composition of f with gamma 0 and sigma 1 is the composition of f with gamma 1. Now, the winding number is something which is preserved by homotopy. I am going to define now a homotopy from sigma 0 to sigma 1 and thereby conclude that W sigma 0 of 0 is the same as W sigma 1 of 0. Recall that the homotopy has to be in C minus 0. So, let me define a new function here g from 0 1 cross AB into C minus 0 given by g of s comma t is equal to f of s comma h of s comma t. Notice that we did put the condition that this is not equal to 0, and being a composition of continuous functions, g is a continuous function and one can check that g is then a homotopy of closed curves in C minus 0 from sigma 0 to sigma 1, and that is going to ensure, and because of that we have W sigma 0 of 0 is equal to W sigma 1 of 0, and that tells us that from star here and star here we get that the number of zeros counting multiplicity is the same for f0 and f1 in the interior of sigma 0 and sigma 1 respectively. Hence we get the result. So, if you notice, all these observations are actually very geometric in its nature. So, it is more easier to understand our setup by looking at the geometry than by looking at the statement itself. If you read these statements without trying to understand what is happening geometrically, it might sound a bit strange. But once the geometric idea is clear, everything actually fits right in place. So, the stability can be captured by the following example. Let us look at an example where our function f of z is equal to z square and gamma of t be equal to e to the power I t for t in 0 to 2 pi. So, we know that z square has a 0 at 0 with order 2. So, the number of zeros in the disk, unit disk with counting multiplicities is going to be 2 here. Now, if you consider a function f epsilon of z, which is say z square plus epsilon. Again, these are all easy examples and it is easy to compute the roots here. So, the roots are going to be what will be the roots here? The roots will be I root epsilon and minus I root epsilon. So for epsilon less than 1, this is going to be in the unit disk, and again we have two zeros of multiplicity 1 each. So the counting multiplicity is the number of zeros is 2. So in this case we have not perturbed our curve. Our homotopy of curves is just going to be equal to h of s comma t equal to gamma of t for all s in 0 1. So in the previous stability of Roshes theorem, and the perturbation of the functions is what was done. And of course, this is a very simple example, but then when we are not able to write down our functions in such a simple manner, we still have that the zeros are a very powerful application of what we just wrote down about the stability of zeros is to prove what is called as the Roshes theorem. Let me write down the theorem and prove it. Roshes theorem. Let gamma be a closed curve which is null homotopic in omega. Suppose f and g are functions holomorphic in omega, and further mod g of z is less than mod f of z in or rather on the image of on gamma. So let me just write it as on gamma. Then f and f plus g have the same number of zeros counting multiplicities. On, let me just be precise this time, 0 1 cross AB, where on the interior of 0 1 cross AB where H is the null homotopy from gamma to a constant path. So just made the notion of interior precise. So the first thing to note is that this condition ensures that both f and f plus g do not have a 0 on gamma, on the curve gamma. Let me give a proof of Roshes theorem. The proof is quite straightforward now that we know the stability of zeros. We will just define homotopy, or rather define capital F of s comma t to be equal to f of t plus s times g of t. Also define our capital H I shouldn't have used, so maybe I should use some other gamma. Let me use gamma here. Capital H is what I will be using from the previous theorem. Define capital H of s comma t to be just equal to gamma of t. I am not going to change this curve at all. Fix that curve. The homotopy is hence going to be the same curve at every stage s. And now if we are to apply the stability of zeros, you can note that h of f of s comma h of s comma t is not going to be 0. Since f of s comma h of s comma t is not equal to 0, we have the number of zeros of f and f plus g in the interior of gamma are equal up to multiplicity. We will solve some problems based on Roshes theorem and see how powerful they are in the problem session that follows.